Hello and welcome to Talking Points. I'm Dave Kelly, Director of Advanced Media Production at Cal State Long Beach. Today we're going to talk about how advanced engineering technology, along with greater understanding of soil composition, can help us better withstand those big earthquakes in the future. My guest today is Dr. Lisa Starr. Dr. Starr is an Assistant Professor of Civil Engineering and Construction Engineering Management. Welcome, Lisa, and thank you for joining us on Talking Points.
Well, I'm happy to be here.
Well, let's begin the conversation by talking about earthquake damage and what we've learned over the past 80 plus years about how buildings perform, how construction performs under sizable earthquakes. What are some of those most important lessons?
Yeah, well, we've really learned a lot over the last 80 years, just based on experience, the earthquakes we've had around the world, especially about construction practices. So we know a lot more now about certain building types that are going to be more vulnerable to earthquake damage, and we can kind of have engineering techniques and building codes that allow us to sort of work around those known problems.
Unreinforced masonry. What is it and why is that a problem?
That's one of the big ones where we have kind of learned about that one early on. Unreinforced masonry is cases where we have what you would think of as kind of a classical brick building. It's called unreinforced because there's no steel or other kind of materials like that that are going to kind of hold the bricks together during an earthquake. So what we've found over the last 80 years or so is that really those unreinforced masonry buildings are our most vulnerable structures. You get earthquake loads on them and they really experience a lot of damage, collapse, and unfortunately loss of life in a lot of cases.
So when we talk about unreinforced masonry and having some metal reinforcement, we're talking about rebar. That's a term people are familiar with.
Yeah, so rebar, you'll hear these days more about reinforced concrete buildings where you have both your concrete and you have that steel, that rebar that's meant to kind of hold everything together during an earthquake. So in places that are really vulnerable to earthquakes like California, we really don't allow those unreinforced masonry buildings anymore. We've moved to safer techniques like steel buildings, reinforced concrete, or wood frame buildings.
And we had a classic example of what happens with unreinforced masonry here in Long Beach during the 1933 Long Beach earthquake. Just to set the stage for that, in 1933, California had really grown over the previous 3 decades, and there was a tremendous building boom between 1900 and the Great Depression. A lot of people moved here from the Midwest. They weren't familiar with earthquakes. So the 33 earthquake was quite a shock, and Lucy Jones from the U.S. Geological Survey has said that the Long Beach earthquake was not just a major seismic event, it was also a major political event because of the impact it had on the California State Legislature. So give us a summary of what actually happened during the 1933 Long Beach earthquake and how it affected the state legislature.
Yeah, the Long Beach earthquake was really a big one for a couple reasons. One is because the population of California had really boomed, especially in the Los Angeles and Long Beach area. So it was the first kind of good-sized earthquake that a lot of people were feeling. It was also important because it caused a lot of damage in some particularly scary ways. What we saw were, especially we had a lot of school buildings that were built out of unreinforced masonry. That was the way it had always been done back on the East Coast, back in the Midwest where people were coming from. So that's what they kind of built when they came out here. Luckily, the earthquake happened in the evening, so school was not in session, but what we saw was extensive damage to the school buildings, full collapses, bricks coming down, and we really think that if school had been in session, it would have been a catastrophic earthquake. As it was, most people were at home. Most homes in California are kind of, single-family wood frame buildings that are much safer. So we got, much less loss of life than we probably would have. It turned in, you mentioned, into a political issue. Anytime you have kind of children involved, that really gets people's attention. So the California legislature was able to pass really very quickly by modern standards, what is known as the Field Act. And the Field Act was really unique because it was the first case where they required special building considerations for schools. So school buildings are required to meet a higher standard than just kind of an ordinary commercial building would these days. It was also, on a technical side, kind of important because it was the first case where we saw kind of special considerations specifically for earthquakes. Normal buildings, under a normal load, you have gravity, it's pushing all your forces straight down onto your building. Earthquakes are kind of special because they're pushing everything to the side. So it was the first kind of codes that required considerations for those, what we call lateral loads. And we've kind of, based on those kind of first landmark steps that we made back in 1933, we've come a long way in, making our requirements for buildings much, much safer.
And the old joke is it takes an act of God for a legislature to actually take action, and this was a classic example of that.
Yeah, definitely. And it's been tremendously successful, too. School buildings are much safer now, and we have not had a loss of life or tremendous damage in buildings that were kind of covered by these improvements in the building code. So it's been one of the major successes of kind of engineering policy, I would say.
And we have some photos of the Long Beach earthquake we're going to take a look at in just a moment. We're not quite ready yet because I wanted to talk about another aspect of earthquake measurement, and that's what's called the Mercalli intensity scale. We know what the magnitude means because Long Beach was about a 6.3 to 6.4 magnitude earthquake. But there's another measurement called Mercalli Institute, which was developed by an Italian volcanologist. That means somebody who studies volcanoes. His name was Giuseppe Mercalli, and he developed this intensity scale to measure the effect. And the Long Beach quake was considered to be a level 8, which is considered severe. What is the Mercalli intensity scale, and what does it measure?
Yeah, so the Mercalli scale gives us kind of a different way to think about earthquakes. Mercalli bases the intensity measure on sort of damage and people's perception of the earthquake. So you have everything all the way from the smallest, which is a 1, which means no one felt it. And we get really hundreds of those every day. They happen all the time. All the way up through the largest earthquake you can get on the Mercalli scale is a level 12, and that is virtually complete destruction of all man-made structures. Most earthquakes, are going to fall somewhere in between. As you said, Long Beach was an 8 because of the really pretty extensive damage that happened to buildings in the area. So the Mercalli scale is useful because it's based on people's perception. You can have earthquakes that get large magnitudes, but if they're out, kind of way out in the desert, the middle of an relatively uninhabited area, you're not going to get very much damage. So those would be high magnitude, low intensity scale. On the other hand, even if you have a relatively modest size earthquake, which the Long Beach earthquake kind of was, but it's located in a highly populated area, you can still get a lot of damage from those. So it gives us a way to kind of judge the damage that comes from an earthquake. It's also nice because it gives us a little bit of, you can use it also for historical earthquakes where we didn't have actual measurements, instrumentation, kind of the technology we have today. You can still get a sense for what that earthquake is like based on, historical records, people's descriptions or perceptions of the earthquake.
So we can measure across the centuries in a sense.
Yeah, we can even use it, historical earthquakes, some regions of the globe have records going back thousands of years, and we can get a sense for how big those earthquakes were based on this intensity scale.
Well, let's take a look at those photos of the Long Beach earthquake from 1933 that I promised. So we've got the first one up here now, and this first one shows a vintage 1933 car that was hit by falling masonry. You can see a gentleman on the left there looking up toward the source of that falling masonry. And let's go to the next slide where we can actually see some of the damage to the schools that you were talking about. This was Pauley High School after the 33 earthquake. What happened here, Lisa?
Yeah, you can see this is one of the cases where they really got pretty extensive damage to one of these school buildings. You can see almost full collapse of that central portion, and how alarming this would have been for parents, grandparents, you know, people in seeing these kinds of pictures in the newspaper or in their neighborhoods and imagining that their kids had been in a school.
Okay, let's go to the next one. This is the John Muir School in Long Beach. This is a photograph that many people have seen in the past. And this is a pretty good example of what happens with unreinforced masonry.
Yeah, this is kind of one of the classical images that sort of inspired our restrictions against unreinforced masonry in earthquake zones. You can see the individual bricks within that facade. The front part of that facade has come down because those bricks just don't hold together very well during an earthquake. And you can even see into the school in this case and kind of the collapse, the partial collapse of the roof in here.
Let's go to the next one. And there we see the Jefferson Junior High School. This is a complete destruction of a school.
Yeah, this is really as bad a collapse as you can imagine. And you can see again, you know, individual brickwork, this unreinforced masonry, and then kind of the collapse of the roof once those masonry walls start to come down.
And if we go to the next picture, we'll see a house. This isn't a school, but it's a house. What causes that house to list like that?
So you can see in the background, we're kind of on a bluff near the ocean here. So this is most likely caused by just a landslide. So the soil, gravity loads are coming, earthquake loads are coming, the soil moves down towards the water. The house is unfortunately on top of that portion of the soil that's moving. So you get really extensive damage when you start to see ground motions this large.
In the next slide, we see that the Navy was actually brought in to help patrol and help out with the cleanup efforts there. You see a sailor in the middle of the shot there patrolling that street. And we see where the actual side of a building came off. Why does the side of a building come off when the other walls are still standing?
Yeah, you see this pretty commonly where kind of the facade is meant to look nice. It's made out of kind of fancy bricks or other masonry, and then that masonry will just sort of peel off from the front of the building during the event of an earthquake.
Let's go to the next one. And this one possibly is in Compton. I know it's at Compton Boulevard and Tamarind Street, according to the writing at the bottom of the screen. And we see sort of the same phenomenon there. Does that mean that there is weak construction in that facade area?
Yeah, so that front facade is the unreinforced masonry, and it just the earthquake comes and it sort of pops away from the front of that building, comes down into the street. This is one of the reasons we don't encourage people to run out of a building during an earthquake.
Okay, well, we've actually got to the point where we're getting ready for the break, but Lisa, before we go to the break, I want you to tell us a little bit about the term liquefaction. What is liquefaction and why is it a concern for coastal areas?
Yeah, so liquefaction is a really interesting phenomenon we see. We commonly see this in sandy soils during an earthquake. What'll happen is if you have relatively loose sand, and you can imagine that sand is kind of filled up with water, during an earthquake, that sand is going to start to shake, and those kind of shaking particles of sand, as they're sort of shimmying around, they sort of lose contact with each other during that earthquake. Once they lose contact with each other, they're sort of floating around in the water, and you get basically sand behaving like a liquid. That's why we call it liquefaction. So that can be a big problem for us if you happen to have a building that's on top of a liquefying soil where that soil is losing a lot of strength.
And on that note, we're going to go to the break, but stay with us. When we come back, we'll take a look at some of the results of liquefaction in the Marina District of San Francisco following the Loma Prieta earthquake. Stay tuned.
Make a difference in our future by researching and helping to preserve our natural resources. The wide variety of careers in this field will have a huge impact on our lives while using the principles of engineering, chemistry, and biology to help find solutions to environmental problems. You could be a part of this exciting field with a degree from Cal State Long Beach.
Welcome back to Talking Points. I'm Dave Kelly. My guest today is Dr. Lisa Starr, and we're talking about earthquakes and liquefaction. Lisa, before we went to the break, you described what liquefaction actually is, and we know that it's kind of porous, loose, sandy soil. We see a lot of this near the coastal areas.
Yeah.
And it's also sand or soil that's been deposited in the last 10,000 years, which makes it part of the Holocene age?
Yeah, it needs to be soil that is starts out fairly loose. So the more recently that soil was put into place, the more likely it is that it's loose and that it's going to liquefy. So the Holocene age, soils that are deposited recently are a big issue. It's also a big issue for soils that are man-made, because of course we're putting it in there very recently, hasn't had a lot of time to densify over time. So we see this a lot in what we call fill, or man-placed soils.
And we have a really good example of what happens with liquefaction in San Francisco in the 1989 Loma Prieta earthquake. So we've got some shots here of the Marina District, and the first one here is sort of an overview shot. What are we looking at here, Lisa?
Yeah, this is a building here where we've had ground shaking, and you should remember the Marina District is quite a distance from what we would think of as the epicenter of this earthquake, which was down closer to Santa Cruz. But because of the Marina District is built on primarily fill material, so it's man-made. It was put in near the turn of the century where we didn't know as much about how to engineer it and how to make sure that it was really strong. So that soil experienced a lot of movement, liquefaction, and unfortunately it led to quite a bit of damage like we see in buildings.
And other than the Bay Bridge, which collapsed, this was probably the area that had the most damage in the San Francisco area.
Yeah, you have a dense population with a lot of buildings that are exposed to the hazard. Again, it's kind of unique because it's this man-made fill that was not well engineered or well understood. So we saw really quite a bit of, in terms of dollar numbers and number of buildings, this was really one of the areas that was most concentrated.
And in the next slide, we have a street level scene there, and we can see the pavement buckling, and what else is going on?
Yeah, so this was a case where the buildings, there was liquefaction happening. Buildings are kind of heavy, so when the soil starts to liquefy and lose strength, the buildings will tend to move down a little bit relative to the sidewalk, pushes all that soil up and out of the way, so that's why we see this buckling happening in the sidewalk.
And in the next slide, we see that the three-quarter perspective of that building, and we can also see that those garage doors are buckling and not safe. That's not a building you want to be in.
No, and this is an example of what we would call a soft story. So the bottom floor here is garages. It doesn't have continuous walls. Continuous walls add a lot of strength to a building. So you have kind of stronger upper floors. Bottom floors are not as strong. So it tends to concentrate a lot of that movement and damage in the bottom floors. And you can see results in a lot of deformation, near collapse, and then kind of, again, facade problems where you have the bricks from up high coming down.
And in the next slide, we see more of the same, and this building has slid and looks like it's a total loss.
Yeah, this is a more extreme example where the bottom floor has experienced a total collapse in this case, and the top floors have come down.
Next slide, we see an example of what's referred to as a sand boil or a sand volcano caused by liquefaction. What is that exactly?
Yeah, so what happens is as the soil particles are moving, they're losing strength. It tends to build up a lot of pressure. And what can happen is that kind of pressurized watery sand will sort of push up through a crack in the soil, and you'll see this material, it ejects just like a volcano. We call it a sand volcano sometimes. So that material kind of comes up to the surface. So this is one of the classic signs we look for. The liquefaction is happening underground, but we can see this kind of surface evidence, and we know, okay, this is an area where we're probably experiencing some liquefaction underneath.
It's a little hard to tell how big that is, but we'll see some examples in scale in a moment that'll give us a real good idea of how large that might be. If we go to the next slide, we see an area along the road in Moss Landing, and Moss Landing is somewhere between Monterey and Santa Cruz. What happened here?
So this is a case where we're getting what we would call lateral spreading. So the idea behind lateral spreading is you have a layer of sand that's liquefying, but on top you probably have something that is maybe a clay material, a soil we don't expect to liquefy. Once the bottom liquefies, that top part is sort of floating along, it sort of goes for a ride, and we can see it spread outward. So that's why we see this kind of cracking, lateral spread behavior.
All right, we're going to go down under now. In the next slide, we're going to Christchurch, New Zealand, and they had a major earthquake in 2011, February of 2011. It was a 6.3 with a Mercalli intensity of 8, which is severe, just like in Long Beach. We're looking at a larger group of sand boils here.
Yeah, so they experienced a tremendous amount of liquefaction in this case. The earthquake was close to the city center, so this is some of the evidence that they saw. There's liquefaction happening underground, and that building up of pressure kind of pushes that soil up to the surface like we see here.
And there's a street level view of liquefaction in the next shot, and there you see it.
Yeah, so this is a pretty extreme case of liquefaction happening. So what's happened is liquefaction is happening underground. It's pushing up that watery sand. You can see how much water is involved in this. And it's sort of flooding into the street. The street is the easiest place for that to go. So it sort of fills up, and you can see this is a lot of material that's coming up out of the ground, enough to cover a car up, you know, at least 6 or 8 inches.
And in the next slide, we see more of the same, and then in the foreground, if you look right there in the center of the foreground, that's an example of how large those sand boils would be.
Yeah, the sand volcanoes, they're usually not tremendously large. It does depend on how much material is coming up, but you can see, in general, a few feet across or maybe 10 feet across. But the combined amount of material coming from all this liquefaction, all these different sand boils, can be enough to cause problems.
And in this shot, it's very impressive to see how that water is just squeezed out of the soil.
Yeah, all that sand and soil had to come from somewhere. So basically, once that material is moving, the rest of the ground has to settle down. So we get, this is basically a pothole opening up in the ground because of that material moving around. And this unfortunate car was the one to discover that pothole.
Right, and so what's happening here is that the earth is just spreading apart or separating?
Yeah, the soil's moving up and out of the way and kind of opening up a pothole in this case.
And speaking of ravines, the next shot gives us another good example of that.
Yeah, so this is an example where everything is sort of moving to the right towards that line of trees there. It opens up a crack in the ground, and we can see kind of just the pavement layers spreading and the soil beneath it.
We're going to switch to Haiti now for the Haiti 2010 earthquake, and this is at the port in Haiti. What is this a classic example of here?
This is again lateral spreading due to liquefaction. So we can see there was a layer that was liquefiable. On top you have kind of the pavement layers that are non-liquefiable, but they sort of float along and go for a ride. As that liquefiable soil moves outward, the top layers move out. And unfortunately, this did a really tremendous amount of damage to their port facility. You can see kind of the container ships, the containers have moved. They lost their it's the only crane on the island that was used for unloading supplies. So it caused a tremendous amount of damage and also difficulty for them in their kind of rebuilding efforts, since they didn't have this port facility available.
And if we go to the next slide, we see a road in Montana. And it kind of has some of the similar look of the previous shot, but this may not be necessarily caused by an earthquake.
Yeah, Montana, they don't get a lot of earthquakes up there. So this is a case where we're getting ground movement, landslide happening. As the landslide moves, it causes cracks and damage to the roadway. But in this case, most likely it's caused by not an earthquake, but rainwater is one of the most common causes. As that water soaks into the ground, it kind of makes the ground both heavier and weaker, and it can trigger this sort of ground damage.
And I guess the point is that the earth can move and can separate for various reasons involving weather and erosion that may not involve an earthquake.
Yeah, it's one of those unfortunate things that we have a lot, as engineers, we have a lot of things to be concerned about.
Okay, and if we go to the next image, we see a grouping of sand boils. Again, it shows that they can be very close together and not very large.
Yeah, this is a case where actually you can kind of see fairly clearly that there was a crack in the top layer of soil. As that crack opened up, it allowed the sand, the watery sand material, to push up, and you see kind of a line of sand volcanoes occurring along that crack.
And if we go to the next slide, we'll see the 1964 Niigata, Japan earthquake. This is a case of liquefaction. What are we looking at?
Yeah, so this is really a case where they had some excellent structural engineering going on. You can see the buildings themselves are really in excellent shape. They're holding together well, but the foundation and soil underneath, they experienced liquefaction, and it wasn't properly designed for that. So these buildings sort of tipped over as that soil lost strength.
So the point is, as I teased in the opening, that you have to have both the advanced engineering technology as well as the understanding of soil composition to be safe.
And we've come a long way since this earthquake happened, where we know we need both the good structural engineering and a solid understanding of our foundations and soils.
Well, let's talk about quicksand for a moment. We have a slide here that certainly looks like quicksand. If we go to the next slide, what do you think?
Again, this is a case where they had, it's basically a pothole opening up in the ground. The car unfortunately found that pothole, and then as the soil was liquefying underneath, it pushed up that sandy soil and sort of filled it in. So this, even though it kind of looks like what we expect from the old adventure game, adventure movies, Indiana Jones, it's not really a case where they were sitting there and suddenly sunk into the ground. It's sort of a pothole opening up and then sort of filling up.
So what actually is quicksand, and is there really a quicksand phenomenon?
You can get cases of quicksand. It basically means something is causing water pressure to build up in your soils, the same way the earthquake shaking causes that to happen, but it's not quite as dramatic or as exciting as we see in the movies. It's really a case where people, especially, it doesn't swallow up people.
Okay, well, let's talk about another phenomenon that occurs in the south, in the southern part of the U.S., particularly in Florida, and that is sinkholes. Are sinkholes in any way related to liquefaction, or is it an entirely different phenomenon?
No, so sinkholes are a different phenomenon, and what we see for sinkholes, especially a lot of the southern states, Florida, Tennessee, Kentucky, there is a lot of limestone in that area. Limestone happens to be, if there is acidic rain, acidic groundwater, it will dissolve. So what happens is, as that water flows through, you get kind of these caves that it's opening up underground. If one of those caves collapses, it can cause a sinkhole to happen at the surface. So we saw a dramatic case of that just a few years ago in the Corvette Museum. Opened up a sinkhole underneath, swallowed up some $1 million Corvettes. So it's a big problem for them, but it's not related to our liquefaction things that we get during earthquakes.
Lisa, unfortunately, we're running out of time. We just have about a minute left. I wanted to ask you about our earthquake readiness and our preparedness. Have we moved further along in this process so that we're much better off today than we might be if something like the 1994 Northridge earthquake should strike?
We're definitely constantly making progress, and we've made a lot of progress over that time. We know a lot more both about the engineering side, how to build buildings that are safer, how to design them so they're safer, but also kind of on the policy side. So we're much better these days about scientists, engineers, and also politicians and first responders working together to identify, things that are going to be of concern, to make plans for what can happen during the earthquake, so that we have, both good buildings ahead of time and also a good plan for what happens after the earthquake.
And for the last 15 seconds, what kind of preparation should people have to prepare for the big one?
I always tell people, if you have nothing else, definitely have water around your house. Water is key. You can't live without it, so make sure you have some stored away. Otherwise, all the things they tell you, medications are definitely important. A little bit of food is good to have too.
And thank you, Lisa. This has been a terrific conversation.
Thank you.
And thank you for joining us on this edition of Talking Points. Be sure to join us for the next episode. Until then, I'm Dave Kelly. Have a nice day.